what I want to do is, in some sense, bridge what you just heard from Stephen Barr and where you're going tomorrow, where you're going more into the biology, evolution, and so on. So what I'm going to try to do in 2 brief lectures is to take you from the very early universe, from the Big Bang, to planet formations, where planets come from. So we'll do that now in the morning. And then from planets to life, both here on Earth and potentially at other planets as well. And in doing that, what I want to do is I want to give you a little bit about where the science stand on these different questions, sort of early universe, planet formation, extraterrestrial life, origins of life, but then interweave with that how we can relate that to theology and philosophy in different ways. And during the Q&A, super happy to dive, of course, deeper into some of those questions. But let's start where we left off sort of 45 minutes ago. That is with the Big Bang. So the cosmos that we live in is the cosmology that we consider being sort of the best explanation of our scientific observation is the Big Bang cosmology, which in some sense is kind of easy to take for granted because it has now been the dominant cosmology for about 70 years or so, 60, 70 years. But it's important to keep in mind that this is not at all obvious that we should be in this cosmology, which in many ways is far more friendly to the Christian story than many of its historical competitors. So if we start with Genesis and with the time that Genesis was noted down, the competing cosmology to sort of both the Christian one and now to the Big Bang cosmology was that you can find in ancient Sumerian and Babylonian texts. It's also something that you would be quite familiar in sort of Greek mythology. This is a cosmology that, in some sense, in size is quite limited, where you have a flat Earth, you have a dome above, you have an underworld, and then everything in the cosmos is spirited in some way. Like there are gods everywhere, god of a waterfall, god of the stars, god of the sun, and so on. This is the cosmos, like the context within which Genesis was conceived, which is important to keep in mind, of course, when we try to interpret what it is that Genesis is actually trying to tell us. And many of the features of this early Middle Eastern cosmology is also recognizable in Genesis, including sort of the overall structure. Again, this sort of like flat sort of plateau almost that is the world within which humans live. Again, this dome above, which is holding back the heavenly waters, the underworld, which also water can sort of bubble up from if God sort of opens the shutters. But what's very different about the biblical cosmology compared to what's going on around it is that sort of all the sort of divinity has been taken out of the material world itself. Now you have a cosmos that's spoken into being by a single all-powerful God, and what used to be gods, so suns and stars, are now lamps. Right? So this is in some sense very de-deified kind of cosmos. But what it has in common with the previous ones, in addition to this sort of overall structure, is that it has a history. It has a clear beginning. It has a very clear development of new creatures coming into existence over time. And this is something we want to keep in mind when we go to the next sort of cosmological competitor, which is that of the Greeks, of Aristotle, that also becomes the medieval main cosmology. So this is a cosmology where you do have a round Earth. So that is something that is well known for a long time. And around the Earth, you have all the heavenly bodies in this eternal orbits. So this is a cosmology that in some sense is the epitome of well-orderedness, where you can see, if you're looking for sort of the finger of God in this cosmology, it is from how law-abiding this cosmos is, that you have things that are going on forever. What is lacking from this cosmos, in some sense, makes it a bit of a challenging marriage with Christian theology, is that this is a naturally eternal universe. There's no obvious beginning or creation story for this kind of Aristotelian and then medieval cosmology. So this one was obviously in some sense married with Christian theology in the Middle Ages, but I would suggest that they should have had a harder time than we do today in trying to figure out where these touchstones between the Christian story and cosmology is. The final competitor has actually a lot of things in common with this Aristotelian medieval framework. And that is the one that came into existence during the Enlightenment, during sort of we're thinking now 16th, 17th, into 18th century, this mechanistic universe, which was sometimes referred to as a clockwork universe, because it's a universe which is governed by laws of physics, which people are extremely impressed by once Newton discovers them, just how gravity seems to rule everything. So in some sense, it seems like you have now a cosmology that, again, once you get it started, okay, you need God to get it started, but once you get it started, it just sort of runs on its own. So it's, again, a universe that is sort of naturally infinite. It has structural differences compared to previous cosmologies. When we have gone here from sort of flat Earth to the Earth at the center, to now the early scientific era, with the help of Copernicus and Galileo, the Earth has been moved into an orbit around the sun. But I would say an equally important thing is that we have gone from a historical universe or historical cosmology to one that seems to be sort of naturally infinite and just existing forever, running on its own, and so on. And this is the backdrop that when we enter into the sort of modern science, that just gives people such a strong intuition, right, that the universe is sort of naturally infinite, which made the Big Bang, the idea of the Big Bang, such a big idea, not just scientifically, but also philosophically and theologically. So the Big Bang cosmology, which we now know is a better scientific model than any of these previous ones, has a lot of interesting features that in some sense it borrows from both these early cosmologies and these later ones. Similar to these early Middle Eastern cosmologies, this is a universe that changes over time, that has in some sense a very natural beginning and a natural flow where you get more and more things over time, much more similar to a story, which is probably part of the explanation, I would say, both why it was a Catholic who came up with it and why it was so quickly accepted by the Catholic Church as an excellent scientific theory. So if you ever need sort of a counterpoint to the one time when I would say the church went in the wrong direction, which would be the Galileo affair, which I know I've already talked about, this is a beautiful counterpoint. But what is the Big Bang cosmology? So obviously you have already heard about this the very sort of beginning, and in some sense how mysterious this very, very early universe is when you start moving towards a point where time starts not really making much sense anymore. I'm going to assume that you already got everything about that from Stephen Barr's lecture, and we're going to start where there's already is clearly a universe in place. But it is a universe that is strange, right? It's a universe that's extremely compact, extremely dense, extremely hot. So that's what we have here. So this is not the beginning. When the Big Bang theory sort of starts and the physics starts, there's already something there, which is important, of course, to keep in mind. Very early on, it is so hot, so energetic that no matter that we have here today can really stay bound together. Atoms cannot stay bound together. The electrons will just be kicked off. Even earlier than that, even sort of the elementary particles like the protons and neutrons cannot be bound together. But as the universe expands, it cools down. And a few 100,000 years after the Big Bang, the universe cools down enough for atoms to start being able to stick together. So you get hydrogen atoms instead of just electrons and protons floating around. These hydrogen atoms now start their sort of like their independent existence from the light, which had previously been basically breaking apart atoms whenever you had a light wave interact with an atom. The breaking apart or the separating of the matter and light we can see today. This is the so-called cosmic microwave background irradiation. This is a very low-level irradiation that is everywhere. The discovery of this radiation in the 1960s was what finally convinced basically everyone that the Big Bang theory was real. Because this was predicted by the Big Bang theory, and the only explanation why we have this very low-level radiation everywhere is from this moment of separation between matter and light very close to the Big Bang. As the universe continues to expand, more and more things can sort of stick together. And somewhere between maybe 100 million, few hundred million years after the Big Bang, the universe is cool enough that some of this hydrogen start gathering in big clouds that start to implode in on themselves. If you have any kind of gas, you basically have two forces that are sort of opposing one another. You have gravity pulling things in, and you have pressure pushing back out. So if it's hot, the pressure is higher. It's going to be more difficult to gravitationally implode. If it gets cooler, it's going to be easier to overcome that pressure force and implode. So what happens is the universe gets colder. Some of these gas clouds start to implode. And as they implode, they warm up. And that's how we form the first stars. These first stars are very large and very short-lived. And they quickly explode into something similar. This is a modern-day stellar explosion, but something similar to this. Finding some of these first stars is one of the major goals of the new space telescope, the James Webb Space Telescope. They have not yet been found, but there is good hope that we will actually be able to find some of them with this amazing new space telescope. These stars, I said, like the reason they're so difficult to find is that they don't live for very long. And once these stars explode, they produce a bunch of new kinds of atoms, which go into forming the next generation of stars, which then appear quite differently. And those are the kind of stars we have with us today. These stars assemble into galaxies. Again, you see here a modern-day galaxy, but also one of the beautiful things about the James Webb Space Telescope, it allows us to peer very far back in time to see some of the very earliest galaxies. And it's continuing to pushing back. And one of the scientific questions that has come up already is it seems like these galaxies start forming earlier than we would predict with the current sort of best theories of the early universe. This is not a catastrophical sort of misprediction of these theories. There are many assumptions that goes into the models of the early universe. So it's not like threatening the Big Bang theory or anything like that. But it seems like there is something in how we're modeling the early universe that's not exactly right, that allows galaxies to show up considerably earlier than we would have expected. Which is also pretty awesome because it allows us to actually look back further in time than would otherwise be possible. Many of the galaxies that we're seeing with James Webb formed within 1 billion years of the universe coming into existence. So there are a couple of things here that I already want to sort of pause and raise as questions where I think science and religion, it's important to talk about both, especially with young students. One, we have already touched upon in earlier lectures, which is to not confuse the Big Bang Theory with the creation out of nothing, which is the first line of Genesis. It might have been, or like at least what preceded, like where the Big Bang Theory sort of starts. This might be, like our universe might be all there is, but we are not sure. And one of the things, of course, we want to avoid is overstating our case. That doesn't mean that the Big Bang is sort of theologically insignificant. It certainly seems to point towards a beginning. And if we ever wanted an image or an icon of what creation out of nothing would look like, I don't think we could have imagined anything better than what nature actually ended up giving us. Which is, also why a lot of the skepticism against the Big Bang Theory when it was first introduced had sort of anti-religious overtones, or sometimes very explicitly anti-religious. And I actually think it's this very providential gift that right as sort of atheism was starting to become the most dominant mode of thinking at the universities, right then is where you get this theory just like falling down and disturbing this whole idea of the possibility of like the infinite universe that's always existed there and seems like to not need God for its existence. As I'm sure you know, and I know Stephen touched upon, an infinite universe still needs a first cause. But there's something about the Big Bang and like actually seeing the universe, like having this apparent beginning, that I think makes it less, it makes it more difficult to forget about it. I think it's easier when you think the universe is infinite to not think about the creator. If you live in a universe that at least has an apparent beginning, it sort of puts it more in front of you, the question of where did it come from. So I think this is one of these like very providential things that happen in the history of science. And this really is, another way to put it is that it brings the contingency of the universe to the foreground. That is, of course, one of the other ways that we can think about trying to prove God's existence. The third way of St. Thomas Aquinas is related to this question. And again, you don't need a beginning for that argument to work, but it does intuitively make it more urgent, I think, to answer that kind of question. At least that's what I found with my students when I teach this as a freshman seminar. The other thing that the Big Bang theory really does, or really gives us, is a universe that has a history, that actually seems sometimes to play out like a story. And this is something that marries very well with what we see in Genesis itself, with sort of the Christian intuition. This doesn't mean that we should try to do sort of very detailed comparisons between the theory of the Big Bang and the story that's presented in Genesis. But I think actually some of those comparisons, if taken somewhat lightly, can be very beautiful. We already talked about the separation of light and matter that happened very early on in the universe. That would be the scientific terminology. I cannot see that without thinking about the separation of light and darkness that happens, one of the first creative acts that God does once the universe is already in existence. And in the same way, when I'm reading Genesis, I think I'm seeing something in my mind that's quite similar to this cosmic microwave background radiation. So it's actually giving me an image of what this sort of creative act could look like. But the most important, I think, is that it suggests that the whole cosmos is a story. And this is something that should resonate, I think, deeply with the Christian imagination when Genesis is presented very much like a story that has first the creation of man as its sort of the reason for existing, and then we find out later in the Bible that it has the creation of a very particular man as the reason for existing. There is a concern that you often hear about the Big Bang cosmology and Christianity. And that is that it seems to make us very small and insignificant. And the historical sort of development would be that, well, we used to think that we were the center of the universe in sort of the Aristotelian medieval kind of context, or even if you go even further back. And perhaps it made sense that God would care that much about us and create sort of the whole universe for us if all he created was the Earth and then some things sort of orbiting around it. But then Galileo came around and he pushed us sort of out from the center to just orbiting the sun, which seems bad enough, though I think it's important to remember that in the medieval and Aristotelian cosmology, being at the center was actually not the good place to be. That was where like the gross things were, like heavy gross. And then the further you went away, sort of more towards the infinite and beautiful you went. If you have read Dante, you'll see like how like he steps through the different levels of heavens and to get closer and closer to God. That at the very end, you get this beautiful inversion that is actually the thing that's the highest up, that's the center of everything, which is one of the real sort of beautiful real sort of moments of sort of literary like imagination, which are deeply theological. Like those kind of, there's several inversions there. I know, it's amazing. But we're going to go back to the solar system. So we move out from the center, but it's still a nice little contained system. Then you get sort of 19th, early 20th century astronomy, which tells us that, well, we're just one of like billions of stars in this large galaxy of stars. And we're actually sort of in the outskirts of that galaxy. So we seem like to have moved from, well, the point, like sort of the center of the universe to somewhere very far away from the center. And then you have contemporary cosmology, which tells us that we're just one out of hundreds of billions of galaxies and not a very impressive galaxy for that. And suddenly, I think for a lot of people, this intuition that God created the universe for us, which is what Genesis seems to strongly indicate, just doesn't seem as plausible anymore. I think there are several, though, ways to approach this to rebuild what I think is a proper intuition. One is that just this idea that the universe is too big, in some sense, is a very sort of human-centric way of thinking about it. If we truly accept that God is infinite, this might be a very nice and cozy little universe rather than a big and cold one. But also the kind of universe that we would want with the laws of physics as they are would have to be big, even if the only living thing in the universe, and we'll talk more about that this afternoon, is us. We would need this size universe, we would need this old kind of universe to exist and be consistent with the laws of physics and chemistry and biology such as they are. But more importantly, I think it's actually a great gift that not just that the universe is so large, but that we now actually know about it. Because I think it is one other, it gives us another way to really appreciate what it is that God has done for us. Though I think it's useful to maybe just take a step back first and realize that this in some sense was always a problem. even for the psalm writer, the universe felt too big and people too small, which is why the psalmist can say that when he looks up and he looks at, I see your heavens, the work of your fingers, the moon and stars that you set in place. What is man that you are mindful of him, and the Son of Man that you care for him? But then the psalmist continues because he knows the truth, which is that yet you have made him little less than a god, crowned him with glory and honor. Now that we know that the universe is even bigger, it should really bring home how amazing it is that God chooses to care about us in the way that he has demonstrated over and over again. But I also think, so I was sort of starting to get to, that this is another one of those icons that contemporary science is giving to us that is theologically really helpful. We cannot imagine what infinity is, or something that is sort of beyond any size or goes on to infinity. When we think about God as this thing that's sort of far beyond anything what we can imagine, I think that can sometimes seem like we don't know what we're talking about. We're sort of just making something up. We can't really explain it in simple ways. It's something that we sometimes get accused of. And I think it's very helpful that contemporary science is showing us that the thing that sometimes we for sure know is real, what we can see with our scientific instruments, the universe, is itself incomprehensibly large. And it provides that icon of infinity, both in terms of its age, but I would say even more in its size. The fact that we can't see the edge of the universe. We can only see that far out because light has only had that long to travel towards us. I think it's actually something that helps us to grasp a little bit better just how immense God is and therefore his gift to us. But at the end of the day, if we think about what is the center of the universe, back in the days, and I would say still today, but if you look again at something like Dante, you'll have the center of the earth is Jerusalem. I don't see why that is still not true. If this is the only place where God has stepped into his creation, it is difficult to think about sort of a place in the universe that would be more at the center of creation. And maybe we'll come back to that a little bit this afternoon when we talk about sort of life both here and on other planets, whether there is just one incarnation. I mean, that is a question that we might want to return to. For the moment, that's hence the question mark. That is not the question mark whether this is the center of the universe if there was only one incarnation, but that is the assumption, of course, that went into it. So that gets us sort of through the early universe and some, I think, of the theological connections that are fruitful to ponder in terms of just the structure, the law-abidingness of the universe, its evolution through time, its sense of a story. What I next want to turn to is the second thing I promised to talk about, which is planets and the origins of planets. The reason we're talking about planets is that I, this afternoon, want to get to life, and to have life, you need to have planets. At least we think so. This is one of the beautiful images that has come down to us from the James Webb Space Telescope. Turns out, as many of the most beautiful ones have to do with how stars and planets form. So this shows a part of the interstellar medium in a nearby galaxy. So we talked about earlier how the first stars, they formed by these gas clouds imploding in on themselves under gravity. That is still how stars form today. So if you look up at the night sky, you see the stars dotting around, and then you just see what looks like darkness in between, like nothingness in between stars. In reality, this space between stars is actually pretty full of stuff. It has gas and it has dust. Much lower density than anything you're used to here, but it's still there. And this gas and dust can be sort of swept up to form different clouds. That looks very similar to kind of clouds that hopefully we will start seeing later this afternoon when it's not completely gray. You can see the blue sky and the clouds in between. And this is a picture of one of these clouds. So you can see this sort of wispy kind of structure that looks very cloud-like, which is why they're called interstellar clouds. But what you can also see in these pictures is that looks like there's this sort of like hole here at the center of the cloud. And that's because part of this cloud has imploded in on itself, formed stars, and then those stars are blowing away the rest of the cloud, creating this cavity that you see here. This is some young stars that are here in the center. So that gets you stars. Then the question is, how do you get to planets? Well, planets form basically as a byproduct of this process. So when one of these clouds, so this is now in cartoon format, one of these clouds collapses in on themselves, they never collapse completely spherically. They always collapse forming a disk. And the reason they do that is that these clouds always have some angular momentum, some spin. And the angular momentum has to be preserved. Now, if you're collapsing a very big cloud to form, in comparison, a tiny star, if you put all of that angular momentum into the star itself, it would spin up so fast that it would be torn apart. So instead, what nature does is that it puts almost all of the mass at the center in the star, and then almost all of the angular momentum in the disk orbiting around it. And we can see the remnants of that in our own solar system, where first of all the planets are in the same plane, so they're all coming out of a disk. But also, almost all of the mass, more than 99% of the mass is in, or 99.9 even, of the mass is in the sun, but almost all of the angular momentum is in Jupiter, the largest planet in the solar system. This disk continues to evolve to form a so-called protoplanetary disk, and it's called protoplanetary because this is the disk where planets are forming in. So planets form from dust and gas in these disks, and you are left with one of these like nice disk-like planetary systems like our own solar system. We can study these disks now. We can see them. Not with a James Webb Space Telescope, but with ground-based telescopes, such as this beautiful one. So this is ALMA. It's down in Chile. It's up at around 5,500 meters, which some of you, well, one of you can maybe translate into American. But it's very, very high up. It's very high up because to study these kind of disks at the wavelengths where we see them most clearly, which is at millimeter wavelengths, you need to not have water in between you and that disk. And our atmosphere has water in it. So you need to be very high up to be above the clouds, but then preferably also in a really dry part of the world where you have very little water vapor in the air to start with. And Chile has these amazing high-altitude deserts, which is where a lot of telescopes are being built today, including this beautiful ALMA telescope, which, as I said, operates at millimeter wavelengths, the same waves that you have in your microwave oven. And if you wonder why microwave ovens work, it's because microwaves interact very strongly with molecules. It gets them to sort of rotate and vibrate. And those same rotations of molecules is what ALMA can study in these protoplanetary disks that are hundreds of light years away. The other thing that emits at millimeter wavelengths is thermal emission. So when you think about thermal emission, you probably think about the infrared, so just a little bit longer wavelengths than the visible. But that's because we are warm. And these disks are much cooler, so they will be emitting most of their thermal emission at longer wavelengths, which again can be studied very well with ALMA. So this is what these protoplanetary disks look like when ALMA studies them. So each of these is a solar system in the making around a young star. So you see this disk of dust and gas. You also very often see that there are some dark lanes where there's material missing in these disks. We think that material is missing because planets are forming there right now, sweeping up the material as they're forming. So this is really seeing sort of solar systems coming into existence as they are forming, which is pretty cool and a new thing as of sort of 6-7 years ago. We also have models of how this happens. So we have these observations that show us it does happen. How it happens is that we start out with some of the interstellar dust that was in these clouds that were collapsing in on themselves. Those tiny dust particles, when they hit one another, they stick. Think about it. These are not little grains of sand, but they're more like the dust that might sort of assemble in a corner of a room. And you see how they sort of build up these sort of large structures, right? That's exactly what happens here. At some point, though, you start getting more compact structure. You start getting pebbles and boulders. These pebbles and boulders can concentrate in the disk and start to have a sort of second gravitational collapse, forming large pebble piles. If these are big enough, they will start forming something that looks like a planet. If you want to form an even bigger planet, like Jupiter, you need this process to be super fast, because then you also need to have time to sweep up a lot of the gas in the disk to form these large gas envelopes. But if you have a planet like the Earth, you can take your time, and this process can take a few million years, up to 100 million years, to go from this dust particles to a full-grown planet. So we know how to form planets, and this is actually an amazing thing. One, because we know it should work, since as of about 20 years ago, we know that this is not the only planetary system. In fact, we think that pretty much every star has planets. And we'll talk a bit more about exoplanets, how we study them, like this afternoon. But for now, all I want to say is that this process should be general. It should lead to planets everywhere. And we do see planets everywhere. And this is an amazing sort of display of how the laws of physics allows you, like, something gives causal powers to dust grains to form planets, to form stable planetary systems. This is something that many great minds thought would be impossible. If you go back and read someone like Newton, who was a very religious man in addition to the questionable theology, but very religious nonetheless, one of his proofs for God's existence was that our solar system was so stable, because he did not think that was possible to do with just the laws of gravity. He thought that was something that God sort of had to come in then and then and sort of restabilize it, so you didn't get sort of chaotic motion and things falling out of place. And now we know that not only can the laws of nature keep it stable, but it can even bring it into existence in this sort of stable configuration. And I think sometimes we get too fixated on looking for miracles to prove God's existence. I mean, I think that is sort of a common theme. While both going back in time, and I think this should still hold today, one of the things that reveals God the most is how amazing the laws of nature are, and the causal powers that have been given to things in the cosmos. And this is something that you see very clearly in the psalmist, as well as in throughout the Old Testament, that when the Israelites are looking for some of this evidence of God, it is often not the miracles. It is often the fact that there is sort of a law and order at all in the universe. And I think, at least in part, this must come out of them living in a context where many of the surrounding civilizations the way they interpreted why you get thunderstorms and why things happen the way they do is because sort of this interventionist deitist making sure it happened. Well, we come out of a context where sort of the competing cosmology is not one with little interventions from deities, but this sort of clockwork kind of cosmos. So we have a very different intuition, but I think it would be good for us to take a step back and realize that, or like to ponder that we cannot at all take for granted that the universe should have these many beautiful laws that all work together to allow for things to come into existence that wasn't there before. And this holds in physics, I think it holds in chemistry, it definitely holds when we come and look at origins of life and on evolution. And there is, I think, a beautiful dignity in the amount of sharing that, or sort of some of this power sharing that God does with his creation. Like just how much, like when we think about why things happen and what's the cause of things. So God is the cause of everything. But there's also real secondary causality in the universe. Like when these pebbles are forming planets, they are really forming planets. And that is something that is not just consistent with Catholic theology, but has been very important for Catholic theology for now a couple of millennia. And it can be compared with some other, both Christian and non-Christian kind of thoughts, where you find a much more sort of focus on that it's only God that is causing things, and that all this other kind of what seems to be causing things are just kind of illusions. But the most traditional Christian interpretation is that no, these things are really causes, and you can think about it a little bit analogous to our free will, that it is possible for us to both have free will and a providential God. And just like that, it is possible to just both have God being the cause of everything, but then all things in creation also having real causal powers to make things be. Another thing that I already touched upon, why, or like where I think star and planet formation fits into sort of theological discussions, is that they are just among the most beautiful things that exist in the universe. Many of these, when you look at Hubble or now James Webb images, basically all you see are stars forming. Whether you're looking at distant galaxies, the reason we can see them is that they're having stars forming in them. All these kind of wispy pictures that I think are the ones that generally sort of catch our imagination are either stars forming or sometimes stars dying, but most of the time stars forming. And if we're thinking about why do we have this universe where things sort of come into existence over time, at least in part, it must be to reveal some of the beauty of God that would not be possible to reveal through other means in a more sort of stable kind of universe. So this gets us to planets, but it doesn't necessarily get us to the planets that we would be the most interested in, which are planets that are somewhat similar to Earth, where you have water, where you have life. For that, we're going to have to now sort of briefly step from physics to chemistry and think a little bit about where molecules come from. The first thing to realize is when we look about the Big Bang cosmologies, it's the same images I've shown you before. At the very beginning, the kind of elements that you have that come into existence at the Big Bang are just hydrogen and helium. If you want to make anything that has other elements into it, you would have to wait until you form this first generation of stars, and then in those stars is where other elements fuse and come into existence. In the very hot cores, both of small stars like our own, but even better in more massive and therefore hotter stars. Once those stars explode, they then spread those new elements throughout their galaxy, and they can become incorporated into molecules into dust, into things that actually make a planet like our own. The elements, if you look at this is a periodic table, if we look at the elements, this means that most of the elements are coming out of stars. So you are a little bit Big Bang. So the hydrogen in you, in your water that's in your body, that's coming directly from the Big Bang. But basically everything else is coming from different kinds of stars, stellar explosions, neutron star mergers, other sort of cool and exotic things. Because, though, these are all sort of secondary processes that happen, like you need to have stars before you start getting these other elements, if we were to plot this periodic table, but now weight it by the abundance you have of each element, it would look something like this instead. So in the universe is basically hydrogen and helium when we're looking at the matter, the normal matter. We haven't even gone into dark matter and dark energy. If you have questions, happy to get to them, but the normal matter, hydrogen and helium. And then the next things that you have are carbon, nitrogen, and oxygen. So not so strange that those are also most of what we are made out of. We're actually a pretty good reflection of what stars have produced in the universe. One of the molecules that's then, well, if we look here, like if you want to make molecules, you can probably guess that some of the most abundant molecules are going to make use of these elements here, carbon, nitrogen, oxygen, and hydrogen. That's going to be sort of what you have the most of. So in light of that, it shouldn't be too surprising that water is one of the most common molecules in the universe. We tend to think about that as something very special to our planet, but it turns out to be incredibly abundant. And when we look towards some of these disks that I was showing you before, and we take spectra of them, we see a lot of lines that's coming from water. So also where other planets are forming, we think water is very, very abundant. There's no real good theology of chemistry yet that I have. Well, I shouldn't say there isn't. I have not learned any really good theology of chemistry as of yet. But I think it is actually something that should be really fruitful to ponder, because chemistry is weird. And it sort of ties together the really microscopic word and the macroscopic one in interesting ways. If you look at the properties of hydrogen and oxygen, extremely different from that of a water molecule. So first of all, when we get chemical reactions, we get completely new things. And this is something that's not completely obvious how you should think about that philosophically, at least in sort of a more classical Aristotelian framework, nor in the more mechanistic sort of modern frameworks either. Once you start bringing water molecules together, though, you again get something really new. Like how a single water molecule, like the properties of a single water molecule versus the properties of a glass of water or an iceberg are not the same. It doesn't mean, of course, that they're not related. They are. It is the sort of very strong polarity of the water molecule that allows you to do hydrogen bonding and therefore start defining what these first clusters of water, how they interact, and why you get such weird properties, such as a water iceberg floating on top of the water. But it is also something quite different. You can't talk about a single water molecule melting, right? This is only a property once you have a very large collection of them. So this is just for you to ponder. I don't have any deep insight beyond that. I think there should be something one should be able to do with this that should be interesting. So where we're going to go this afternoon is then what we want to put in this water to potentially get to an origins of life. But I instead want to spend the last sort of like 10 minutes before we go into questions in taking a step back and talking a bit more about science, the scientific method and its limitations, and how one can start having that dialogue with students. One of the things that I think that I noticed with incoming students at Harvard is that they often think about science as knowledge. and every other kind of knowledge is sort of like bad science. And I think that is a very important thing to have very direct and honest discussions about with students. So I want to talk a little bit about that. The first thing that I thought would be good is just to sort of go through together very, very briefly sort of how we typically present the scientific method, and therefore what some of the assumptions and therefore limitations are of it. So this is our typical circle of the scientific method. We start with a question. And in my example here, because astronomer, so I'm going to just take the sun. The sun is shining. Why is the sun shining? It's a good question. Many 3-year-olds have the same. The rational thing to do is to then look into what's known about sort of related topics. How much does it shine? What's its luminosity? Are there different ways to produce energy that we already know about that we could perhaps hypothesize is a good way to make the sun shine? And at the end of that, you should, through some creative, slightly mysterious event, you come up with a hypothesis. And one hypothesis which would be quite reasonable is to say, well, the sun looks like a big fiery ball. Maybe it works like a fire here on Earth, like a candle, like a very big candle. And the fire, here it's the conversion of chemical energy. You're breaking and forming bonds, releases energy, and that gets you luminosity of a candle. Now, the next step is to test this through some experiment or observation. What we would want to do is to say, well, is there enough molecules? Could there be enough molecules in the sun to generate the luminosity of the sun, which is with this sort of chemical conversion, like we have in a candle? If you weigh the sun, you will find out that there's enough matter in the sun to keep it burning this way for most sort of 100,000 years. This actually was quite fine up until sort of the 18th century or even early 19th century, when we didn't know how old the sun and the earth was. This was a perfectly reasonable kind of assumption. But then starting with geology and eventually astronomy and cosmology, we came to realize that the earth is almost 5 billion years, and therefore by inference the sun as well. So then this couldn't work anymore. So we need a new idea. And the new idea is fusion, right? That instead of getting chemical energy, you get energy from fusing hydrogen together to form helium. This is how energy is actually generated in the sun. And now if you do the same calculation, you see how much energy you can get from each sort of transformation. You weigh the sun, and you find that through this method, you could have the sun burning for 10 billion years. This is a great way to take steps forward in science, and we have learned tons through some version of this method. In reality, for those of you who are scientists, you know that it's not as straightforward as this. There are many things here that are a little bit weird, and we often sort of skip steps or go back and forth rather than to go in this nice circle. This here is the most mysterious of all, like the hypothesis. Why did Einstein come up with this idea of E equals mc squared and not other people? This is not explained by science, right? So there are many things already in this circle that is somewhat mysterious. And I would say often there's going to be backward errors as well as forward when you actually do this work. And many scientists don't want to test their hypothesis as carefully as they should, but luckily other scientists do, and so on. So this is not every project is going to look like this. But still a very, very powerful method that has given us many both useful results as well as taught us a lot about the universe around us. And one of the most recent ones is actually a test of this of the theories of relativity when they managed to image the black hole first in another galaxy and now in the center of our galaxy, which just shows that scientists go back to the same theories and try to apply harder and harder tests to them to see if they still work. So science is amazing, but there is many sort of limitations with this. One is the historical and sort of ideological context, which really colors what kind of questions that we ask and how we interpret the evidence. When Copernicus first suggested that the Earth was orbiting the sun, that was within a long history of people just taking for granted that the sun was orbiting the Earth. It's going to take a lot of evidence to convince people to switch such a radical, switch their sort of whole worldview in such a radical way. Copernicus didn't have the evidence. Galileo didn't really have the evidence. But through a combination of sort of increasing number of observations, as well as just the beauty of this new idea, it took about 100, 200 years, everyone basically changed from one to the other. But it took much longer than maybe we should think, because there was this big sort of cultural and ideological kind of intuition that you needed to overcome. Something similar happened when the Big Bang theory was first introduced. It took some time, maybe longer than it should have, for people to accept it as the cosmological framework within which to live. Fun fact, the way that the expansion of the universe was discovered was observations of galaxies looking redder than they should, which implied that they were moving away. This was a discovery of Hubble. Hubble died not believing the Big Bang theory was real. And again, it's like looking back, it might seem like he should have realized if the universe is expanding, it needs to expand out of something small. But this again was in a context where the infinite universe was taken for granted. And Hubble actually even doubted whether the galaxies were really moving away. He thought there might be other explanations for why they looked red as well. So we have to think about the sort of cultural context and what it sort of takes to break through it. In this case, Lemaitre, and perhaps his Catholic intuition helped. Who knows? I would like to believe that that is true, that many other people must have had the same idea pop into their head of what an expanding universe looks like if you sort of reverse time. But maybe for him, it was a little bit harder to dismiss it because he already had in his mind the idea that the universe has a beginning and has that much more story-like quality than many of his contemporaries. Another limitation of science is its sort of domain of applicability. As you might be able to tell, I like Italy a lot. So this is one of several pieces of Italian art I'll be using as examples in the coming hours. Trying to explain the Pietà with science would be silly. So then I think most people would actually agree with that. You can start trying to make some measurements with how he managed to polish the marbles. It has this sort of otherworldly kind of radiance. But I think most people agree that you're not going to get very far. So then the question comes, can you then not learn anything from studying the Pietà? And I think for anyone who has seen it or even see it like this, I think that should also strike you as silly. One of many, many examples of knowledge that we can gain that is not scientific. You can really learn about what it means to be human by reading Shakespeare, but it is not scientific knowledge. If you want to make a political decision, you can be informed by decision, but ultimately you're going to have to apply sort of a political kind of intuition and knowledge to take that prudential decision. And if you want to understand which questions that belong to the domain of science versus other, you're going to have to be reasoning philosophically rather than scientifically, which is then another limitation of science. I think that's the next. I'm going to jump back and forth. Okay, apparently I skipped that slide. Which is another limitation of science, is that in some sense, what science is not the scientific question. Why science should work is not the scientific question. That relies on sort of philosophical understanding of what the scientific project is. There are many things that cannot be understood or proven through the scientific method. I just showed the Pietà, but the existence of God would be another one. Doesn't mean, again, that you can't use science to inform your reasoning around it. I just gave you a whole presentation of how I think scientific knowledge can be brought into theology in a way that is really sort of mutually beneficial. But ultimately, God is not, a material object that you can sort of do experiments on and therefore get those observations that would prove that he is doing or not doing what you want to demonstrate. Even things that seem more material do not necessarily have a scientific explanation. There are at least two sort of origins, which go beyond the material, beyond the scientific. The origins of the whole created order would be one of them. Might be somewhat, like I said, might be just our universe, or it might be some superstructure, but whatever it is that came out of nothing, that is beyond the domain of science. But also, if you hold, as we should hold, that we have an immortal soul, that is also something that's created directly out of nothing. That is not something that can be studied scientifically, even though some of the effects of it, again, you can have science inform your reasoning about it. Even things that could have a sort of scientific explanation sometimes don't. Miracles are real, and if you were trying to use science to explain why Jesus could walk on water, like with some, surface tension argument or something like that, you would go astray. That would not be the appropriate way to interpret the miracle. Again, happy to go in more depth about miracles and maybe some of the obstacles that they present, but the important thing is that even all material things are not within the domain of science. I mean, sometimes miracles work as signs because they do the unexpected. They are, in some sense, derivative of a scientific or at least sort of normal understanding of the universe. If it was normal that people could walk on water, it would not be a miracle or a sign that Jesus walked on water. And that's also why when there is a miraculous healing, we can use the contemporary medical science to assess whether this claim is likely or not. So again, you can definitely have science inform, but it is not sort of the main way of getting to that kind of knowledge. Well, I did keep this one. But the most maybe fundamental limit of science is that it's not independent of other forms of knowing. We already touched about the philosophical one. Again, Rome. It's a beautiful, beautiful place to visit. We already talked about the philosophical foundations of science, that why the scientific method that I just showed you, why that should work, that is a philosophical claim. But there's also, I would say, an even deeper sort of theological foundation, which is why should you trust that there is this strong connection between the things around you and the things that you are thinking inside of you? Why should you trust that your mind has a way to tell the truth of things? From pure evolution, there's no reason that should be the case. Our brains can be shaped by evolutionary pressure to do things that makes it easier for us to survive and find food and things like that. But there's no reason that we should trust it to reveal truths about the universe. However, if we believe that our soul is directly created by God to be in the image of likeness of God, I think it suddenly makes a whole lot more sense that it seems like the kind of patterns that we see outside in the universe, the laws of nature and so on, that we can actually grasp them and sort of retell them in our mind as well. So to end this lecture, there are multiple ways that the scientific project and the theological project, I think, can interact in beautiful ways when we look at these sort of the cosmos as a whole, or what kind of cosmology that we live in. But one of the things I think is the most important to do first, even though I did it last, is to figure out, like help the students understand what is the distinctions of different ways of knowing, and that there really are different ways of knowing. And it's not just science and sort of bad science, but that there are really things you can learn through things like theology, philosophy, literature, art, that are impossible to get through the scientific method. And that is not because they are sort of less important, but that is actually where many of the most important questions are answered. And with that, thank you, and happy to take any questions. Okay, so wait for the microphone.
You set the microphone.
Okay.
Thank you. Oh my gosh, I have so many questions, but I'm only going to ask two related little ones. So we know what we can see in the observable universe, correct? And there then must be some unobservable part of the universe. Do we have any estimations as to how large that actually is? And if we do, what is that comprised of? And then the second question is, we know that we have an expanding universe that's accelerating. What is it expanding into? And if there are boundaries to the universe, and if there are, do we have any idea what, I don't even know how to use words to describe it, what that outside those boundaries, what it's expanding into is?
Yeah, so these would have been great questions to ask Stephen instead, so I'll have a crack at it. So a couple of different things. So there are two ways to think about sort of the visible universe or observable universe. One is what kind of matter we can see, or like what part of the universe, sort of the scope of the universe that we can see, how much of it can we actually see? And the answer there is a pretty small percentage. So most of the universe is not made up of these beautiful stars and galaxies. It's made up out of dark matter and dark energy, which we don't know what it is, but it's really important and basically governing everything. So there's some left for physics and cosmology to do. So that's just like within sort of the span that we can see, like we can't see most of the things. The furthest we can see is on the order sort of 70, 80 billion light years. And that's boundaries set by how fast light can travel plus the expansion of the universe. And as far as we can see, things look the same as they do locally. It seems to follow the same laws, seems to have the same kind of things in it. So we can't see any boundary. And because we can't see any boundary, we can't see, in some sense, what's outside. But even if we could see further, the way to think about sort of whether our universe is infinite or bound is like we're not going to see a physical boundary, right? Because it is the three-dimensional space itself that has some sort of boundary. So a bound universe would be the best analog to that is that you think that pretend you're a two-dimensional creature, you're living on the surface of a ball or a donut, and you walk around. So this has a limited size, but you will never get to the end of it. So now we can't imagine that as sort of three-dimensional space because we're three-dimensional creatures, but that's sort of the best analog for what the sort of a non-infinite universe would seem like to us. So we're not expanding into something is the hard part. I mean, we might be part of some superstructure, but as far as we can tell, the universe, it's all that there is. So it is the universe itself that's growing in size, which again is like impossible to imagine how sort of a three-dimensional thing is growing into size. So ask Stephen next time. I'm sure he has some good analogy for it, because he's more of a cosmologist than I am. I just do planets.
Thank you.
I've got a question relating to Earth. Is Earth, the planet itself, is it like a form thing, or is it still like collecting dust, or is it like completed?
The Earth completed its formation with a caveat about 100 million years after the sun formed. So it was fully formed within 100 million years. Now in the case, and that's true for all the other planets as well. Now there is a tiny bit of debris hanging out in the solar system. It's most impressively in the asteroid belt and then in the Kuiper belt that's further out. But this is very little mass compared to any of the planets. So this is really just some leftover. And when we get sort of a meteorite or something like that, it's so small compared to the mass of the Earth that you wouldn't have that, think about that as part of it being forming, even though we can get a little bit of new sort of matter ending up on the Earth. The caveat in the case of the Earth is that we were fully formed sort of within about 100 million years, but shortly thereafter, we had an impact, a really giant impact, a Mars-sized object that hit the Earth, which, as you can imagine, completely ruined the surface of the Earth. A lot of the material from that impact went into orbit around the Earth and ended up forming the moon, which is why we have such a big moon compared to any of the other Earth-sized planets. It's from this catastrophic impact. So in some sense, you could say that maybe the Earth wasn't fully formed until that was over, but we're still talking, within 100 to 200 million years of when the Earth and the Sun started forming. I think it's.
Thanks so much, Karin. This is kind of a philosophical question.
Go for it.
But in your field, what is the reason, like the rationale for studying cosmology? Because it seems at first blush, as someone who's not in this field, that there's not a direct instrumental explanation the way there might be for, same with the medical sciences and even physics. And I wonder, is that explanation for why we study these things, why we want to study these things intuitively? We look at this and it's amazing, and I wish I studied this. If I had the capacity, I would. Is the answer to that related to this more general topic of the complementarity between cosmology and faith?
Yeah, it's a great question. So in the university, they often refer to this kind of science, basically everything that I presented, as curiosity-driven science. That is like the actual term that they use, which is then distinct from the sciences that have some sort of application in goal, like finding a vaccine or something like that, where it's there's something sort of, in some sense, obviously useful as the end point, even if the journey there might be very, very long. And often you will see in the biological sciences and in engineering, like they might be doing very fundamental things, but they often, if in their grant applications, they often have the sort of the end goal is to do something to improve the human condition. Like that is the end goal, which is like really good. It's not what I do. I do the other part. And I think it is a beautiful thing about the university that there is this realization that they are there, I think, today to do both. They're there both to help go from sort of fundamental science to things that really does improve the human condition, but also just to learn more truths about the universe. And I think if you see many of the universities, like they grew out of sort of religious schools, like that's why they have all these seals that have often truth or light or something like that in their mottos. So Harvard is veritas, it is truth. And that in some sense is the core of the university. It's actually this more curiosity-driven or sort of truth-oriented. We just want to understand better what kind of creatures we are, what the universe is like, and that is the core. And then, if something good comes out of it, even better. I think now in the modern one, it's more sort of 50-50. But a lot of the origin comes from this theological mission towards truth that then also became sort of a scientific mission as the sort of modern scientific project really took off.
Karin, you have one online, so you can look towards the camera when you respond. In regards to an infinite universe, I'm wondering if scientists base their science on the ancient philosophical understanding of the universe being, quote, unquote, infinite, like ancient man and philosophers felt that God was infinite. Was it similar to how you said that people in ancient Greece had the god of the waterfall, just thinking about how science possibly took from ancient mythology for once? Is that possible?
So I'm not sure I fully understand the question. So I might just use it as a step-up point to talk about the topic as a whole. Because I think in part it might just be a historical question. That is like, how did science develop, and sort of what sort of intuitions did it pick up along the way as sort of human knowledge advanced? And I don't know the answer to that question. But I think what is, in some sense, fascinating is that you do have, I think Greece is a good example, and I think the contemporary world might be another good example, that you can have sort of mythology and sort of a philosophical, scientific worldview coexisting in the word. So it's not like this is a completely linear process. I mean, in ancient Greece, you have the god of the waterfalls, and you also have Plato. I mean, they are contemporaneous, right? I think in today's society, you do have, in some sense, both the scientific explanations and, I would say, classical Christianity that has both this reverence for reason and for sort of trying to find the truth using reason. You also have a lot of magical thinking going on, whether it is sort of outspoken or not. So I don't think that necessarily this is something that happens in a linear way through time. I do think what is special about, if you just look through it historically, what is pretty special about the scientific project is where it happened. So the scientific project, it began in Europe, and there's a lot of debate on why it did, right? So you have other civilizations who are in many ways just as advanced as Europe in the 16th and 17th century that did not have the scientific revolution. China being the most obvious example, which had many what we would call scientific discoveries before they happened in Europe, or at least engineering discoveries. And why did they not move from those initial discoveries into a proper scientific revolution? And one of the ideas is that why this didn't happen is that the context in Europe was that of the monotheists, which, as well as the sort of the Greek sort of philosophical monotheistic inheritance. So it's funny, right? If you read Plato or Aristotle, on the one hand, they have the whole Greek sort of mythological inheritance, but when they talk about God, it is something much more similar to a monotheistic God than sort of the gods of the waterfalls, right? So you have that inheritance and the intuition that there is one God that's behind it all, that has set up these laws of nature that we might be able to uncover. And when you look at many of the early scientists, people like Newton, I mean, it's a prime example, but this holds for most of them. A lot of their motivation comes from uncovering these divine laws that they think are imprinted in creation. So it matters what kind of sort of religious intuitions you have for whether you're going to invest in this scientific project. So my guess is that is probably more important than, in some sense, this sort of God of the waterfalls kind of intuition. since in that kind of word, like if you think that everything has sort of deities in it, there's no reason that they should operate according to some pattern. We know that people are very difficult to predict, and if you think that a waterfall is like a person, you wouldn't try to come up with a law that governs that waterfall. So getting rid of all these deities and introducing one universal lawgiver is something that should give you more confidence in that it's worth pursuing this kind of scientific project. I have absolutely no idea if that was part of your question, but it made me think of it, so thank you anyway.
Hi, I really loved what you said. I've never thought about it before, and I'm coming at this more from like a math perspective. I don't know if this is under your umbrella, but like, is there like a probability for my phrase is like conditions to be perfect, where you know the correct ratio of elements to come out, and then the right, you mentioned like the inertia of the rotation around the sun, and then the amount of dust, and then I'm going out of order, the new stars, and then they don't last long, and the new galaxies, all of that, like for all of that to then, you know, like boom, Earth, like I'm assuming the probability of that is so low, and from a math perspective, right, where like if the probability is so low, like it can't be an accident. Or is that anywhere in the conversation?
Yes, but I would be careful where I put the not accident part. I think it's maybe, so there's a big picture kind of thing. We're talking about the laws of nature, why they are the way they are. And again, this is like so Stephen's wheelhouse, so you should get hold of him again. But I'll do my best to impersonate him. So there's like, or not. There's a big picture kind of place where I think this is a real conversation to be had, and a very, actually an ongoing one, which is when we look at the laws of nature, they all have these constants in them, which are not given by the laws themselves. Things like the charge of the electron, at least the ratios between these different sort of element, like these different constants. We don't know where they come from. They're not prescribed by the laws. It's something we have discovered, like what they are. If they were slightly different, or at least the ratios were slightly different, we would not have atoms beyond hydrogen, and then obviously we wouldn't be able to form things like the Earth. We would have, if other ratios were off, the universe would be extremely short-lived, so we would not get this nice big expansion that we're seeing. And when you look at all the ratios that had to sort of add up, it starts to seem extremely improbable that they would have those ratios if this is sort of if they could have other numbers, but we're the one chance of a universe. There are a couple of possible solutions people have proposed to this. One is that these numbers do vary, and we're just one of many universes, so we're just a lucky one, basically. Which, when we come to planets, that's actually not a terrible argument. But it, of course, makes the big assumption that there are many, many other universes. So you have to sort of invent billions and billions of universes to get around it, which is not as ad hoc as it sounds. There are some theories of that's related to the Big Bang that would actually suggest that maybe there are many of these other, that we're part of this sort of superstructure, our universe is part of this superstructure. But even so, then we would still live in a really weird universe where these parameters are tunable so that then and then you do get this sort of perfect universe. So I would say, like in both cases, it's weird, and it's not the proof for God, but I think it points more towards God than it points away from him. Once you have the laws of nature as they exist, there are many things that sort of fall into place. I mean, one of them, I said, is that planets form so readily. Like so once those constants are in place, planets do form. And they form very easily just because of conservation of angular momentum and because of electrostatic effects between atoms and dust and so on.
It's kind of like an autopilot, just set it, forget it.
Yeah, yeah. I mean, and that is an amazing thing. So I would say the amazing thing is not at this sort of later stage. It is that the laws of nature are such as they are, and that's what allows structure in the universe in general from galaxies. So galaxies also rotate. That's why they look sort of disk-like, many of them, to the formation of these protoplanetary disks, to the formation of the planets themselves. And I do think it is worth pondering, and it is an amazing thing, that it seems like it's a very small number or sort of very basic laws of nature that sort of, as the universe is unfolding, gives, well, rise to this amazing like wealth of structures, including planets. And I say many theoretical physicists therefore have this intuition that there is like one ultimate law of physics that they're really aiming to find, like a theory for everything, or of everything, and that is sort of the true goal in some sense of theoretical physics. I think that's a laudable goal, but it's a very monotheistic goal. I mean, like that is an intuition that I think would be difficult to have in a polytheistic kind of context, right? So there is something there that's definitely worth pondering, and I think, yeah, is better for Christianity than it's worse. But I wouldn't go all the way to saying that it's a proof.